Okay, our final speaker of the session is Tia Ruza from University of Waterloo. She'll be talking about asymptotics of multivariate algebraic generating functions.
Yeah, thank you for the kind introduction. So the work I'm talking about today is joint work with Torrin Greenwood, who we heard from earlier today, Stephen Meltzer, and Mark Wilson. So in particular, Andrew talked about rational generating functions. Now we're moving on to algebraic generating functions and how we can find those asymptotics. So let's just give some motivation. What's the type of question we might be asking when we're considering this? So here's an example question. We have binary trees. How many non-empty planar rooted binary trees are there with n vertices and k leaves? So here I have some non-empty planar rooted binary trees with 3 vertices. 4 of them have 1 leaf. 1 of them has 2 leaves. And in order to do this, we take a look at the multivariate generating function. So similar to what we saw in Torrin's talk with the bivariate generating function, we have our coefficient bkn, which is going to be the number of non-empty planar rooted binary trees with n vertices, k leaves. Our u to the k there is, the k is going to be the number of leaves, and then we have z to the n, where z is going to be representing our vertices. We can use a typical construction. We saw an example of one of those in Torrin's talk. To get this, I won't go through the details of this construction, but using that construction and the quadratic formula, we can get an explicit generating function that we see here. So this is all fine and dandy, but the real step or complicated step is to go from this explicit generating function to these asymptotics here. And so that's kind of the main stuff that I'll be talking about today, is how we can go between the two of them. And here I've given just asymptotics for when the number of leaves is 1/3 the total of vertices. But I could have gone in a different direction entirely. I could have said, okay, what if I have half the number of leaves, the number of vertices, etc. So as Andrew mentioned, we have to kind of choose a certain direction to go and look at our asymptotics for. So I keep saying algebraic function. If that doesn't twig something in your memory, just a reminder, an algebraic function is the root of some polynomial that can be expressed. So we usually call the polynomial the minimal polynomial of whatever our algebraic function is, and that's going to be really important. So I'm going to keep saying minimal polynomial. And when I use the bold Z notation there, that just means there could be more than one variable. I might have Z1, Z2, Z3, all the way up to ZD for some random D. So if I start with a multivariate series, Andrew mentioned this in his talk, we do need to look kind of like at an R diagonal. I'm also going to be talking about diagonals for looking at embedding stuff. So I really want to make sure that this definition is clear. So say I'm looking at an R diagonal. This, for example, is the main diagonal, that 1, 1 direction. So the direction is 1, 1. So I'm going to take terms that have powers of x to the n, y to the n. So in this case, we have 1 because that's x to 0, y to 0, 2 xy because x to 1, y to the 1, 6 x squared, y squared, etc. And I can do the same thing for other diagonals. So here I have the 2, 1 diagonal, which is the same premise. It just doesn't get a fancy name because we don't use it quite as often. So it's a little sad about that, but that's okay. So those are the definitions of diagonal. But I want to kind of go step back a little bit about these generating function classes. So Andrew mentioned rationals. So all rational generating functions are algebraic. All algebraic generating functions are rational diagonals, which are all D-finite, which are all D-algebraic. And there's even stuff that's not D-algebraic. But I'm looking at, or we were just looking at specifically algebraic generating functions and how we might compute those asymptotics. So we're taking, a little step out. So as Andrew mentioned, most of the time for rational generating functions, we got it, right? We can use Andrew's code. It's all great. It's all fine and dandy. But for algebraic, we're not quite there yet. And so this is work towards that, kind of making it a little bit more automatic for people to get these results. Let's go back and give a little bit of a history of what's happened so far prior to some of the stuff I'll mention for algebraic generating functions. And when I say a history, I'm not saying that Bender is the first to work for it, but just the first work that I'm not talking about today in more detail. So in 1973, Bender had some results for a central limit theorem from what I'll call local expansions in 2 variables. And so local expansions just means that if you can rewrite your algebraic generating function in a certain way, then you can prove that it has a central limit theorem. 10 years later, in 1983, Bender and Richman came up with the result for a central limit theorem and asymptotics from, again, this idea of local expansions, which I won't go into more details of, in general variables. So now it's not just two variables, but general variables. And work in 2015, 2018, Torin came up with asymptotics for a certain kind of class, or a certain type of algebraic generating function that looks a certain way. But the question that we kind of want to consider is, okay, what if we don't actually have an explicit generating function? So I said, this is what our generating function for algebraic looks like, but really they're just embedded in this minimal polynomial. So say I just have this minimal polynomial and some initial terms of my generating function. Can I still calculate asymptotics? And if so, how? So that's kind of the question that we're looking at and kind of characterizing these methods that don't actually need an explicit generating function for it. So I'll look at kind of two big overarching classes of how we approach this. And the first is asymptotics via embeddings. And so what I mean by this, I'm going to give a bunch of different theorems and a bunch of different methods for doing this. But essentially, the root of it is I have some algebraic generating function. I'm going to embed it as a diagonal in a rational generating function. So say, for example, I need to look at a certain diagonal of that rational generating function. But if I do that, then I'm going to get the asymptotics of my initial algebraic generating function. And as we know, calculating asymptotics for rational generating functions is not so bad. And so we can do that. So this is this one class. I'll talk about another class of kind of approaches later. So the first work towards this kind of rational embedding idea was done by Furstenberg in 1967. And this is where I mentioned wasn't necessarily talking about the first work when I said 1973. And Furstenberg showed that if you have some algebraic generating function f of x that vanishes at the origin and it has some minimal polynomial, where if I take the partial derivative in terms of y, that's what I mean by this sub y here, that's partial derivative at 0, then that's non-zero. Then if both of those conditions are satisfied, we can get that f of x is in fact the main diagonal of this rational expression here. And again, this is always going to be rational because p is a minimal polynomial. It's a polynomial. This is certainly going to be a polynomial over a polynomial. And that's that main diagonal, so that's that 1, 1 diagonal. So when I'm looking at my coefficients there, my original coefficient of x to the n is going to be the coefficient of x to the n, y to the n in my embedding. Let's do an example of that. A classic example is the Catalan generating function, which has a minimal polynomial x y squared minus y plus 1. We take the partial derivative of that. That's 2xy minus 1. Great, it's not 0 at 0, but the Catalan generating function does have a non-zero constant, right? Its constant is 1. So how do we fix this in order to be able to apply Furstenberg? And how we do this is through a method called pre-processing. And if you're going at a completely naive approach, your first guess might be to just say, okay, well, let's just subtract off the constant. I'm looking at asymptotics here. I don't really care what that constant is. And even if I did, I know what this constant is. I'm not looking to figure it out. And so we can do that. We can subtract 1 off f of x, embed for that diagonal, and just add that 1 back in later. So that's great. But it's not the only way that we could have done this. The second, slightly less naive approach would be to just say, let's multiply it by x, right? Again, that removes our constant. Once again, we can embed the diagonal. This one, looks maybe a little prettier than the last one. And we can still post-process and figure out what exactly our asymptotics are from there. But either way, once we do this embedding, it's relatively straightforward to get an asymptotic expansion, beginning with 4 to the n times 1 over n to the 3 over 2 times root pi. And this can be derived completely automatically from either of those two expressions. There. All right. So this is great, but you might have noticed I said I was doing stuff for multivariate. This is a univariate formula. So how do we do this with multivariate generating functions? And it turns out it generalizes very naturally to basically the exact same formula or theorem. So if we have, and this should say algebraic generating function, f of x, where its constant is 0, and we have the minimal polynomial, such that when I take the partial derivative in terms of y, at 0, it's non-zero, then we get that the coefficient of x to the r of f of x is going to be equal to the coefficient of x to the r times y to the power of, I'm going to add up all the different exponents on my variables from r of this embedding, which looks exactly the same. And so, you might be saying, okay, this looks almost identical. Why is the first one different in terms of this like adding up? We don't have to do the adding up. Well, in the univariate, there's only one variable. And so adding one variable just ends up being the same as the one variable. So in fact, Furstenberg, as I showed it originally, is just a specification of this generalization.
Is the proof of this essentially as easy as the proof of Furstenberg?
Essentially, yeah. Like it's basically use partial derivatives. The proof of Furstenberg is like a couple lines. Proof of this maybe slightly longer, but not yeah. Very straightforward. It follows very naturally. In fact, in the original paper, like Furstenberg could have proved based off of this. He just wasn't looking at stuff that needed that, so it wasn't there. Yeah. But okay, so I showed ways for if we don't have a constant that's 0. But what if I don't have the other condition, right? What if I don't have that the partial derivative of my minimal polynomial at 0 is equal to 0? How do I handle this case? So Denef and Lipschitz came up with an approach in 1987 that says, okay, we'll let f of x be some algebraic generating function. Then there exists phi of x and a rational, or algebraic phi of x and rational w of xy, such that phi at 0 is equal to 0. The minimal polynomial of phi satisfies that constraint, and f of x is equal to w of x at phi of x. So essentially, we're kind of building phi of x is like our new f, q is our kind of new p, and it satisfies the conditions of this embedding. And then we can basically directly apply Furstenberg with some modifications for the fact that we've changed now our f there. So in particular, they did this using something called finite Étale extensions. I don't have a lot of background in that, but the point that I want to make about how they did this is that it wasn't effective. It wasn't constructive. It exists. They've proven that, but they haven't told us how to get that. So that's the main concern with this Denef and Lipschitz. But for relatively simple examples, it can be great, right? It's exactly Furstenberg when we set phi equal to f and w equal to y, which is great. So it does the exact same thing. If we want to pre-process, so say we have a constant that is in fact non-zero, we want to just subtract it off, we can just set phi to be equal to f minus 1 and w to be equal to y plus 1. So that's great. We can do the other pre-processing. The phi is equal to f of x and w is equal to y over x. And the benefit of this is that originally with just applying Furstenberg directly, we needed to do kind of some post-processing to remember how we actually did that pre-processing. But here, Denef Lipschitz wraps it all up together so that we get our direct embedding. And we can do an example that's slightly more complicated. So the other examples with the pre-processing don't necessarily have the issue where when I take that partial derivative at 0, it's 0. But this is an example which does, right? If I take the partial derivative of this minimal polynomial, I just get 2y at 0. That is indeed 0. But I can fix this with using Denef Lipschitz. So let's set phi is equal to 1 minus root of 1 minus x minus y. W is equal to x times 1 minus y. And you can do a quick double check. If you sub in phi for y there, it does indeed get us back our original f. And then our minimal polynomial of phi is indeed non-zero at 0 when we take that partial derivative. Thanks to that, we can use Denef Lipschitz to get our lovely embedding where the coefficient of x to the r, y to the s in our original function is the same as the coefficient of x to the r, y to the s, capital Y to the r plus s in our embedded function. And thanks to that, we can relatively straightforwardly get some asymptotics for it. But again, how did I get that? You know, I did some computations. I kind of guessed a little bit, figured it out. In some scenarios, you know, we have some methods for getting this, but it's not, can't really just do that for anything. So is there an effective way to get this? And indeed there is. So Safonov in 2000 said, okay, if we have an algebraic generating function where the constant term is 0, so that condition's back in there, then there's a computable rational function r of x, y, and a unimodular matrix A such that the coefficient of x to the r in f of x ends up being the coefficient of x to the a times r times y to the a times r, where again, we're adding up each of those different terms in the vector in order to get a result. And so this time, it's actually computable. We don't have to guess. And the idea behind it is an effective resolution of singularities, which is done by setting y is equal to w plus sq of x. And this is kind of where the idea of, I said I wanted some initial terms of my generating function. So sq of x here is just the terms of my generating function up to degree q. So I don't need my entire generating function, but I do need some of those terms. And then using some repeated monomial transformations of the form shown on the slide, then we can get to the point where we are essentially back to using Dnef-Lipschitz and doing this embedding. So I won't go into too much detail about that, but know that it's algorithmic. In fact, we have an algorithm made in Sage that you can just put in your generating function and it computes the Safanov embedding for it. So let's do an example of this where Safanov might be able to be used. And this is polygon dissections. So a dissection of a polygon is an arrangement of diagonals, not the same diagonals that I talked about earlier that do not intersect. So here, this is two diagonals, they don't intersect. One diagonal, this intersects, but this one intersects, so it's no good. But the other two are diagonals. So Valona in 2018 said, okay, the generating function for enumerating polygon dissections by these 2 points is indeed algebraic. And the 2 points that I went over was the number of vertices and occurrences of a finite set of 2 connected patterns. And a 2 connected pattern is just a graph that's 2 connected. 2 connected graph is a graph where if you remove any vertex, it's still connected. And so an example of this is the generating function counting dissections by the number of vertices and the number of triangles, or 3 cycles. And this satisfies this minimal polynomial here. And we can indeed apply Safanov's algorithm to get an embedding. Now, it's kind of a big embedding, it's a little gross, but it is an embedding as a rational function, and we can indeed determine asymptotics for this in a fixed direction. So that was the last of the embedding methods that I'm going to mention. And so the key with those is that they're kind of nice, right? We can embed stuff pretty quickly, doesn't take much, there's not a lot of conditions on them. But the downside is that, okay, they do give you that embedding, but then you still have to find the asymptotics of the rational generating functions, which are pretty easy to do most of the time, but sometimes the embeddings aren't nice. And we run into some of the cases that Andrew was talking about in terms of getting those asymptotics. So the implicit method is a different method, and it has more restrictions on when it can be used, but it does give you asymptotics automatically from using this method. So there's pros and cons. So I'll give a little bit of an idea of the implicit method. I won't go into too much detail. It's rather complicated. But again, we start with the Cauchy integral, as Andrew mentioned, but this can actually be rewritten. So instead of integrating over t, we can integrate over t tilde, where t tilde is a set xy, such that x is an element of t and y is equal to f at x. And so in particular, this means that t tilde is a subset of the singular variety of p. So if you think about it, since p is the minimal polynomial of f, anytime I sub in those, it's going to be 0. And so we can use this to our advantage. If we remove the branch cuts of f, but we can only deform t tilde with inside the set of p that goes to 0, so inside that variety of p. So similar to what Andrew was saying, you do these deformations and then you have this parameterization, you take that integral. Instead, we often deform still in t, but then you lift to the deformation in t tilde, which then makes computing that integral easier. So again, didn't go into too much detail about that, but this is work done by Baryshnikov, Jen, and Pimentel in 2024, showing how to apply ACSV in this framework. Both Robin and Yuli are here this week, so I encourage you to ask them if you have any questions about this method, as it's really interesting and it does apply to a lot of different results. But our work is implementing this as an algorithm so that it can be used without necessarily understanding the inner workings of it. So I want to take the last few minutes just to go over some examples of how we might apply these these methods for calculating asymptotics. So the first example I have here is bar graphs. This is work from Bousquet-Milot and Reichnesser in 2003. And we have a collection of columns that lie on the x-axis, and an edge on the boundary is called an external edge. So the bar graph looks kind of how you would expect a bar graph to look, but those bold lines here are what we call our external edges. And we want to enumerate the number of bar graphs where X is going to be counting our horizontal external edges and Y is going to be counting our vertical external edges. In that case, we can get a minimal polynomial here as follows. And we'll notice that, our function has no constant term. That's great. And indeed, when we take the partial derivative of our minimal polynomial at 0, it's equal to 1. That's not 0. So we can directly apply Furstenberg or Dinaff-Lipschitz as Furstenberg, where we set Q is our minimal polynomial P and W is equal to Y, and get an embedding for this. And then thanks to this embedding, we can get asymptotics relatively directly, since it's a relatively nice embedding. And I do want to mention, as I said before, sometimes the embeddings are really nice, sometimes they're not so nice. And one of the things that we want to keep working on is figuring out how to make these embeddings nicer, right? Is there pre-processing things that we can do in order to make these embeddings nicer? We haven't yet found how to do that. Another example that I have here is a Catalan refinement. So this is the Narayana generating function, g of x, y. And this enumerates a bunch of different things, such as rooted ordered trees by edges and leaves, dig paths by semi-length and number of peaks, and much more. But if we subtract off 1, then this satisfies the hypothesis of Safanov. So again, recall Dinaff-Lipschitz got rid of the hypothesis that we needed initially for our function to have a 0 constant, but Safanov added that back in, so we do need to do a little bit of pre-processing just for that. So subtracting off that 1, and then we get this lovely embedding here. And here I have asymptotics for when the exponent on X is twice the exponent on Y. Another example is bicolored Motzkin paths. This is from Elizalde in 2021. So these are lattice paths from 0, 0 to 0k. And they're similar to the Motzkin paths that Torin was talking about. They never go below the x-axis, but instead they have 4 different types of steps. You can take an up step, a down step, or a horizontal step of the first color, or a horizontal step of the second color. So hopefully those colors kind of show up, but essentially I've chosen 2 different colors. It doesn't matter which horizontal step is which color for this example, just that there is 2 colored steps. And we say we want to enumerate the number of paths where X counts the number of down steps plus the horizontal steps of the first color, and Y counts the number of up steps plus the horizontal steps of the second color. We get a lovely generating function, and we can apply the implicit method. So this is briefly kind of how the approach works. But again, you can just use the code, type in your generating function and get your results. But here we have only one minimal critical point on the branch in the direction that we're looking at for asymptotics. We notice that the branch defining F is the lower of the 2 branches. This allows us to kind of figure out which branch we're looking at and apply that lifting properly to get our results. And this gets us some asymptotics like this. And I just want to highlight, so I'm showing different methods for different examples. This does not mean the other methods don't work for these examples. I'm just not going to show you every single method for every single example. Another example is assembly trees. So there's a variety of different things we can do with this. So assembly trees are from Bona and Vince in 2013. And so this is where, given a connected graph G, an assembly tree is a rooted tree with the vertices labeled as subsets of the vertex set of G. So here I have a graph G. Here we have vertices 1, 2, 3, and 4. And how the labels of these trees work, so these are each assembly trees. So T1 is an assembly tree, and T2 is another assembly tree. So each leaf is a singleton. So I have 1, 2, 3, 4, 1, 2, 3, 4. Each non-leaf has to have at least 2 children, and it's labeled by the union of the labels of its children. So for example, this point here is going to be 1, 2, and then this one here is going to be 3, 4. And then similarly here, this is 1, 2, this is 1, 2, 3. And finally, the root is labeled with the vertex set of G. And so that means the number of leaves that you have has to be at least the size of your graph in terms of the number of vertices, but also that it's rooted, it kind of goes back up to the top. So in these examples, this is going to be 1, 2, 3, 4, and this is also going to be 1, 2, 3, 4 because they're constructed based on the same graph. So that's great. I've defined the problem, but really we want to enumerate the number of assembly trees, in this case in the complete bipartite graph. where X counts the number of vertices in the one partition. Oh, sorry, yes.
Where is the structure of the graph going into the assembly tree? Just a set of vertices?
Yeah, I also have the same question. There may be like from other analysis that they're doing from it, but I didn't see where that structure came in. Yeah. So say we want to enumerate the number of assembly trees in the complete bipartite graph, then we'll have X counting the vertices of the first partition, Y counting the vertices of the other partition, and we get an algebraic generating function f of x, y. We can embed this as a minimal, because the minimal polynomial satisfies all of our requirements, and get this embedding. We can also use the implicit method. Turns out that the minimal point corresponding to our direction can be lifted, it's all good. And either way, we get the exact same asymptotics, which is what we should hope for, here we have the asymptotics of when the size of these two partitions is the same. The final example I'll show is for new and old leaves in plane trees. So this is an example from Chen, Duch, and Elizalde in 2006. So here, the old leaves are the leftmost children of any node. The young leaves are those that are not leftmost. So here, like these are the non-leftmost of this node here. This one, it's an only child, so it's technically the leftmost leaf. Here, it's the second child, it's not leftmost. So then it's a young leaf. And here we have two leaves again, leftmost and not leftmost. We want to enumerate the number of these trees where X counts the number of old leaves, Y counts the number of young leaves, and Z counts the number of edges. And now we again get a algebraic generating function. Chose this example because my other ones were all bivariate, but we do actually have non-bivariate examples as well, and it does work the same way. We can embed this using f of x, y, z minus 1, and it satisfies all of our requirements. Get our embedding, and again, find asymptotics. In this case, I chose a direction where the number of leftmost leaves is half of the number of young leaves, which is 1/3 of the total number of edges there. So we have lots more examples than what I showed. I think I counted yesterday. I think we have 75 generating functions that we're doing these results for. So this includes, but it's not limited to, trees that are plane description trees, Schroeder trees, planar maps, lattice paths and quarter plane walks, dict paths with air pockets, valleys, that should say Motzkin paths with plateaus. Dict paths don't have plateaus, quadrangulations, non-crossing partitions, Ising models, RNA secondary structures, pattern avoiding permutations, Hardian arrays, and much more. But at the same time, we want more. So if you're looking at this talk and you're like, hey, I have an algebraic generating function that's multivariate that I would love some asymptotics for, please feel free to email me or come up and chat with me, or in the question time, mention it. And we want to add more variety even still to these examples. So with that, I'll say thank you.